This is Mr. Baker, and we are finally on the last of our 5 review worksheets for the end of course test. Well, last if this is the last of the videos you've watched. This is operations with polynomials and probability, 2 completely unrelated topics, but just a few practice problems from each thrown onto the same worksheet. We start out with a polynomial problem, really 2 polynomial problems. We're supposed to factor both of these, and those techniques are going to be different because they are different looking polynomials. This one has 3 terms, this one has 2 terms. So their techniques will be different, but we have to do both of those without a calculator, which shouldn't be too hard. These numbers don't get too big on us. So for the 3-term polynomial, we need to start out by making it into 4 terms, because 3 terms, we can't group it up like we'd like to. We want 4 terms. So the first and last term aren't going to change, but that middle term gets split into 2 things. And those 2 numbers are going to be P and Q. Now, they both get an X every time. They're still X terms, just like the 9X was. But we need a P and a Q value. And we get 2 hints for that. P times Q is going to multiply to be the first number times the last number, 2 times -5. Don't forget that negative. 2 times -5 is -10. So I'm looking for 2 numbers that multiply to be -10 and that add to be the middle number, which is 9. So 2 numbers that multiply to be -10 add to be +9. Well, if these 2 numbers multiply to be negative, we know that means that they're going to be 1 positive and 1 negative. That's the only way I'm going to multiply 2 numbers and get a negative. But if they're going to add to be positive, if you add a positive and a negative, you get the sign from the bigger number. So the positive must be our bigger number. The only options to multiply to be 10 are 1 and 10 or 2 and 5. Put the negative with the smaller of the 2 numbers, and those are our options. Now we can figure out which ones add up to be 9, and that's going to be -1 and +10. And it doesn't matter which one of those 2 numbers you put where. I think it's probably easier, at least we make fewer sign mistakes if we put the negative number in the first blank. I'm going to go ahead and put the 10 in the first blank, put the negative in the second blank, just to show it works fine either way. The whole reason we did this, though, is so that we can group these out. We want to have 2 groups of 2, and that's why we wanted 4 terms. We didn't think to look for a greatest common factor in the beginning. That really should have been our first step, and it didn't have one. But definitely now, this pair has a greatest common factor. As a matter of fact, 2 and x both go into 2x squared and 10x. We can divide each of those by that 2x to see what's left. It's going to leave us with x plus 5. The second pair, same idea. Now, they don't have a whole lot in common. They both are negative, but that's about it. Nothing else is going to go into 1x and 5 other than that negative. But if they have nothing else in common, we can always pull out a 1. And remember, anytime that first term's negative, whether the second one is or not, we want to pull out that negative. So -1 times x plus 5. Why is it plus? Because when I pull out that negative, I'm dividing by -1 to see what's left, and that's going to change both of those signs. This is a really good time to stop and check to make sure things are going right for you. If they're going right, that means your 2 parentheses are going to be the same. So maybe you forgot and you ended up with an x minus 5. Then you would have seen, hey, these parentheses aren't the same. You go back and see what you've done wrong. So now that I know that they're the same, though, I only need that x plus 5 once. Just 1 x plus 5. I do need another set of parentheses, but what's going to be in it? Well, that's the stuff we pulled out, the 2x and the -1. So x plus 5 times 2x minus 1. There's a lot of other things we can do with a factoring problem. If this had been equal to 0, we might then set each chunk equal to 0, get an x's lie thing going on there. But we don't have to do that. All it wanted was us to factor it, so all we need are these 2 sets of parentheses. Moving on to this second problem, now it's only got two terms, and there's not much we can do with two terms. We can always try to find a greatest common factor, but nothing goes into 16 and 25. But there is one thing that we can do when it's a binomial if it fits the right pattern, and this one does. It's a difference of squares, which is to say that the first number or the first term and the last term are each perfect squares. What can I square to get 16x squared? Well, I square a 4 to get 16. I square an x to get x squared. So 4x is my first building block. It's where the 16x squared came from. What do I square to get 25? Or you could ask, what's the square root of 25? Same concept. The square root of 25 is 5. So those are my two perfect squares. That's why it's a difference of squares. And it has to be a difference, which is to say that has to be a minus. If this was a sum of squares, if we were adding them, it wouldn't factor at all. But when it does have a minus there, these will factor into conjugates. 1 plus, 1 minus, but otherwise the parentheses are exactly the same and built from these building blocks we just found, which means they're both going to start with 4x. They're both going to end with 5. 4x plus 5, 4x minus 5. That's how we factor our difference of squares. Every single time turn into conjugates. Changing gears to a probability problem. Again, no calculator, but we shouldn't need calculators on this. This is a two-way table problem. Now, two-way tables often signal that we're going to have a conditional probability, a probability with given stuff. But the word given doesn't show up here. None of these are conditional probability. They're just and or problems, which is fine. Two-way tables work fine for that as well. Now, anytime we're working with a two-way table, we do want to make sure we've got our totals from our rows and columns. And this table didn't give them to us. Sometimes it will. More often than not, we have to find our own. So let's add some stuff up for our ham, turkey, and veggie, for our mayo and mustard. We've got all those totals, just a little bit of adding, and no, you shouldn't need a calculator to add 3 one-digit numbers. But when we add these up, whether we add up across the bottom or down the right side, we should get the same sum. So it's two ways we can add it, and they both give us 35. So that's our grand total, and that's going to be really important, especially because it's not conditional probability. So let's look at A. Now that we've got those totals, it asks, what's the probability a sandwich has turkey and mayo? Well, anytime it's asking for probability, we're looking to put together a fraction. Even if it wants a percent, you're going to get that percent by putting together a fraction. And our fraction is going to be the targets over the possible, or the good ones, the ones we're after, over how many there could be. So let's start by figuring out what we're looking for. Turkey and mayo. So here's the mayo, here's the turkey. We want the ones that are both. We want the and stuff. Now, and does often mean multiply, but not in this case, because when you're working from a two-way table, we're not multiplying, we're just finding where those two things overlap. Where is it turkey and mayo? There's just 8 of those right there. So 8 sandwiches that are going to make me happy, that's what goes on top. How many sandwiches could there be? Well, we're not in a conditional probability problem. There's nothing given. So it could have been any sandwich I grabbed. So 35, that's how many sandwiches are our total. Anytime it's not conditional probability, that grand total is our denominator. So that's our probability, 8 over 35. We can try to reduce that, but nothing goes into 8 and 35. Now, B is an OR problem. And OR problems mean that we're going to add. And even with a two-way table, there is going to be some adding going on, definitely. And it's still going to be a fraction, and the denominator is still going to be that grand total, but we are going to have to add some stuff up. So this time we're looking for what's the probability that it's veggie or mustard. So there's our mustard, there's our veggie, and it doesn't have to be both. We just want it to either be a veggie sandwich or a mustard sandwich. Both is fine, but if it's got one or the other, and that's why we're adding. How many veggie sandwiches are there? 10 veggie sandwiches. How many mustard sandwiches are there? 18 mustard sandwiches, and we're going to add those together. The question becomes, could it be both sandwiches? Did we count any of those sandwiches twice? And we did. Part of that 10 are those 6 veggie and mustard sandwiches. Part of that 18 are those 6 veggie and mustard sandwiches. So yes, it could happen, and we've counted 6 sandwiches twice. So we've got too many sandwiches added up there. What do I do about it? Well, I can just subtract how many sandwiches we counted twice, which is going to be the ones that were veggie and mustard. And that's 6 sandwiches. So we're going to subtract that 6. So 10 plus 18 minus 6. And that's going to give us 22 sandwiches over the 35. So 22 sandwiches are mustard or veggie. And you could have added this up by individual boxes instead. You could have said, hey, there's 18 mustard sandwiches, and just add in those 4 more that were veggie that didn't have mustard, and that would have gotten us to 22 as well. But regardless of how we get there, we're going to get 22 over 35 for our probability. Again, that's not going to reduce, so that's our answer. Number 3 is definitely a weird problem, and it's a non-calculator problem, which is fine. As a matter of fact, that's the point of the problem, is trying to get us to take some algebra and use it to help us multiply some numbers in very special cases. And this is definitely one of those special cases. So, so the calculator is not going to come up on this. We're not really going to need it. Although a number line, sketching ourselves a number line might help. And let's put the 37 and 43 both on that number line. So 37, I can throw that anywhere, and then we can just keep counting from there. 38, 39, 40, 41, 42, there's 43. So why does that help? Well, this is going to give me some slightly different ways to represent these numbers. What is halfway in between 37 and 43? Well, that's going to be 40. 40 is halfway between 37 and 43. And what we're going to do is we're going to use that 40 to help represent both 37 and 43. How do we do that? Well, 40 is, since it's halfway in between, it is the same distance on the number line from 43 as it is from 37. It's 3 away in each direction. So if I'm multiplying 37 times 43, 37 is really 40 minus 3. And 43 is really 40 plus 3. You may be starting to see some of where this is going. 40 minus 3, 40 plus 3 sounds an awful lot like x plus y and x minus y, especially if we swap their order, make it x minus y, x plus y. That means to multiply these, I can make the x be my 40, and the y be my 3. So x is 40 and y is 3. To finish this problem out for you, what it's really doing is trying to get you to do the mental arithmetic here. Instead of multiplying these, x plus y times x minus y is really x squared minus y squared. In other words, this is going to be 40 squared minus 3 squared, squared. 40 squared is 1600, minus 3 squared is 9. You can tell I'm using a mouse to write, and this is really ugly, but 1600 minus 9, I can do that in my head. That's going to be 1595. 1. So now, did we have to do any of that? No, we didn't have to do any of that part. None of that was asked in the question. I just wanted to go through and make you aware of why this kind of question would come up. Because this is one of our standards. We're supposed to talk about how to relate the form of some algebra stuff to actual arithmetic. And this is really the only problem I can think of that would do this with the difference of squares or with anything else, which means, since this is one of my standards and I can't think of any other way to really hit the nail on the head for what they're asking, I think there's a really, really solid chance that this exact problem is going to come up on your end of course test. That's why I'm talking twice as long on this one as working it out was, because all we really have to do is, if they ask us to do something like this, find what's halfway in between the numbers and figure out what I'd have to add and subtract to get there, and that's how we fill these in. Now, they might ask it in a different way. They might ask you to do a little bit more of what we were doing over here about why we would do it, but I would definitely expect to see a problem like this show up on your end of course test. All right, back to probability again, another two-way table. This time it is conditional probability. This time we are working with those givens. But once again, as with any two-way table, let's get our adding up. Now, grade, we don't have to add up the grades, but we do want to add up all of our yeses and our nos and add up how many people there are, but you don't want to do 9 plus 10 plus 11 plus 12. That's 9th grade, 10th grade, 11th grade, 12th grade. I saw one or two people do that, get a little carried away with their addition. And then you can check, make sure by adding these totals two ways for that two-way table, they really do both give us 172. Your worksheet probably says 170 up here because I had a typo on it. Probably had a typo in here, but it's much easier to just go ahead and fix the total. So what is the probability that a student believes in ghosts given that they are in the 10th grade? So it was a yes or no question, do you believe in ghosts? So given that they're in the 10th grade, what are we given? That they're in the 10th grade, so only 10th graders matter. None of the rest of that table matters to part A here. So when I set up my fraction, it's always the target over possible. My possible is just that grand total, not the grand total of everybody, but just the total of 10th graders. So 42 is going on the bottom of that. What goes on the top? Well, the number of people that fit the category that we're looking for. Technically, it's they fit the 10th graders, and yes, that they do believe in ghosts. But since we're only looking at 10th graders, we just want to target those yeses. That's 24 of those. That goes in the top of my fraction. Is that my answer? Well, it's how I build my answer, but most of the time we want to simplify these. If it doesn't say otherwise, you want to simplify it. So what goes into both of those? They're both even. Divide them both by 2. Wouldn't be quite enough, though. We can divide them both by 6, or maybe divide by 2 and by 3. That'll get us down to 4 over 7. Now B, same kind of problem, but different given. This time we are given that they do not believe in ghosts. So we're given that they answered this question, no. So the only part of the table that matters to us are the no's. So when I set up this fraction, the number on the bottom, 82. That's how many no's we had. The number on top is going to be how many 9th graders were there that were no's. Because it's asking about 9th graders. So 22 of those. And again, we can simplify this one. This time it is just dividing by 2. It's going to give us 11 over 41. Conditional probability on a two-way table, pretty much always the same thing. It's that and over given. Back to polynomials, another no calculator problem, but we shouldn't need a calculator on this one either. We're just doing some multiplying on the first one, and it looks like the answer to a factoring problem with the 2 parentheses, but that's what multiplying polynomials looks like. So all you got to do there, that's our double distributing. Foiling, if you prefer to say that, I don't. So we're going to distribute that 3x. 3x times 2x squared, that's 6x cubed. 3x times negative 7 is negative 21x. Then distribute the 5. 5 times 2x squared is 10x squared. 5 times negative 7 is negative 35. And now we combine like terms, except there are no like terms. Now, most of the time we do get some like terms with these distributing problems, but this time we didn't. They all came out with their own powers of x, or like the negative 35, no x at all. So this is a perfectly fine answer. Now, be careful with your directions, because the directions might ask you to put them in descending order of powers of x, in which case you would want the biggest power of x first. Or if it was a multiple choice problem, usually that's how they list it. If that's the case, we do have a couple things in the wrong order. There's nothing wrong with this answer, but if they're specific about it or you're looking to match it to a multiple choice answer, you might need to switch the order around, put the x squared term before the x term. But otherwise, perfectly fine answer either direction. Now, this second problem, a lot of people are going to come down here and start trying to distribute all these things, but we don't need to. This is a subtraction problem, not a multiplication problem. If we're going to subtract, that's just going to be a matter of combining like terms. Now, there is one thing I do need to distribute. It's not any of those terms, it's just the negative. Subtraction is adding the opposite, so we need to distribute the negative. And now I can combine like terms. What like terms do we have? Well, we've got those x cubed terms. 4x cubed plus negative 1x cubed is going to be 3x cubed. Now be careful here, because that negative 7x and that positive 17x squared are not like terms. We're used to being able to find our like terms, and they come up that way a lot, but these aren't like terms, so they're going to be different. So minus 7x plus 17x squared. If they're not like terms, they can't combine. So the last two like terms we do have already highlighted for us. The constants, 11 plus negative 15. 11 plus negative 15 is going to be negative 4. So we've got our like terms combined, so that's our answer. Once again, just based on the order I wrote things down, I ended up with my x term in front of my x squared term. Nothing wrong with that, but sometimes it's worth having them in the other order. Another probability problem. This one, there's probably a few different ways to tackle this marble problem. I'm going to do it the way that we've worked with the most often in class, and that's using our formulas, specifically our OR formula, which is probability of A or B is probability of A plus probability of B minus the probability of A and B both happening. So let's figure that out. So the probability that it's clear or cracked, let's start with the probability that it's clear. That's 18 clear marbles out of 60, so 18 over 60. No reason to reduce that right now. Plus the probability that it's cracked. Now, the problem actually tells me what the probability that it's cracked is, and that's half of the marbles are cracked, so there's a 1/2 probability that I'm picking a cracked marble. Now, it doesn't say half of the clear marbles are cracked. It doesn't say half the opaque marbles are cracked. It says half of the marbles are cracked. And with that information, we have to assume that it's 1/2 regardless of what it is. So we can multiply our probability for what we subtract, but we have to subtract that probability of it being both. So 18 over 60 times 1 over 2. That's our OR probability formula, 18 over 60 plus 1 over 2 minus 18 over 60 times 1 over 2. And then to simplify that, since I'm adding, I probably want a common denominator, and I can make my common denominator be 60. I can be a little bit sneaky with how I do this and probability part. Multiplying this is just 18 times 1/2, which is 9, 60 times 1, which is 60, so that and probability becomes 9/60. So 18 over 60 plus 30 over 60, that was 48 over 60 minus 9 over 60 is going to be 39 over 60. Now we can reduce that. 3 goes into both of those. That is 13 over 20. Always reduce your fractions, but that's our answer. There are other ways to have worked this problem that may seem like they're easier. For instance, yeah, there's 18 marbles that are clear. Half of the marbles, which means 30, are cracked, minus the 9, half of the 18. That would be clear and cracked, and then just put that all over 60 just once. I wanted to do it this way because we never know what kind of problem they're going to throw at us on the end of course test. It might be one that just gives us probabilities instead of raw numbers. Part B here, if you select 2 marbles at random, what is the probability that both are opaque? Well, opaque means not clear. But the big word to pay attention to first is both. What does that mean? Well, that means the first one's going to be opaque and the second one's going to be opaque. And probability means we're going to multiply. Now, it also says we're picking 2 marbles. Never says we're putting one back, so we're going to assume that we don't. If it doesn't say you're putting it back, then you're picking it and keeping it. Even if you pick 2 at the same time, you know, it's like you picked the first one and kept it. So this formula actually isn't quite accurate. It's actually the probability of A times the probability of B given that A happened. In other words, the probability fractions are going to change. We have to think about it and think that what we wanted to happen the first time did happen when I'm setting up the second fraction. So first let's figure out how many opaque marbles there are. 60 minus the 18 that are clear is going to give us 42 opaque marbles. So that probability that the first one's opaque, 42 over 60. That's the easy one to set up. And I need the second fraction, but I need to think about that one. I assume I got what I was after. So there were 42 opaque marbles. I got one of them. Now there's 41 of those left. There were 60 marbles. I definitely picked a marble already, so now we're down to 59 marbles left. And it's because it was and, we are multiplying. We multiply these. We get 287 over 590. Now that's already reduced because I multiply on the calculator. That just didn't seem like one I wanted to multiply out by hand and then try to reduce from there. So if you wanted a percent, that's going to be 48.6%. You would actually just take 287 divided by 590. To get that, it would give you 0.486 and then move the decimal 2 to the right. It didn't ask for a percent, but when you get a big ugly fraction like this, sometimes it just makes you feel better to see what a percent is. I would want the fraction, though, is what I'd be looking for. Number 7 at last. No calculators on this one, but again, why would we need one? Marissa's putting in a garden in her backyard. The length of the garden needs to be 1 foot less than twice the width in feet. Now, this really isn't anything more than an integrated 1 problem. We could certainly be asked to do things like this, especially if we were going to do more with it. But it's not a very hard problem. It's just hard to do if you just try to jump right to the answer. Whenever you're dealing with a concept like this, you definitely want to draw a picture. So let's draw a picture. There's my garden. Please don't spend the time to draw in the carrots and lettuce and everything. I didn't. I just found this on the internet and pasted it here. But we just need to be able to come up with the area of that. Well, area is length times width. And it talks about both those. It says the width is W. So we're going to have a W, and the second sentence does tell us as a function of W, so W is going to be in there somewhere. So what's the length? Well, it says the length of the garden needs to be 1 foot less than twice the width. Let's start with twice the width. Twice means you do it 2 times. That's 2 times the width. But that's not everything. It's 1 foot less than twice the width. So take that twice the width, and I need one less than that, so I'm going to subtract 1. 2w minus 1, and that is going to be my length. So the area is going to be length times width. I just need to multiply those. So that's 2w times 1 is my length, or 2w minus 1, excuse me, is my length. W is my width, and I multiply them. And that's honestly an answer. Or I could switch it around. Some people like the W out front first, or some people would want to distribute it and call it 2w squared minus w. But it didn't say anything about what form we wanted to put it in. Any one of those is a perfectly good answer. If you were doing a multiple choice problem, it might ask you to find all the functions that would be that, which means all of these could be things that you were looking for. It might be that you have to match it up. It might tell you to simplify it, which means get rid of the parentheses, which means this one would have to be your answer. So sometimes you do get to pick what form it's in. Sometimes they really shoehorn you in with their directions or making it a multiple choice problem. So yeah, this one was a little bit all over the place because it was some probability and some polynomials, but lots of practice, and hopefully this was the last one. You've looked at all of our videos, you're ready to go, and Wednesday is our first day of testing, Thursday if you're a second day blocker, but get a good night's sleep and do your best on the test.